Time to start doing some actual numerical methods now that we're a week in. So we're going to start by talking about root finding problems. So this is the material from chapter 2. Okay, so what's the goal? The goal is that we have some nonlinear function, f of x, and we want to find the root of it. That is the value of alpha such that f of x is equal to 0. And we're going to assume at least that f is a continuous function. Yeah?
When you say f of alpha equals 0?
Then so we're given this equation, f of x equals 0, and then alpha will be the solution of this. So yes, f of alpha equals 0. Okay, we can ask what does the conditioning of this look like? Right, so when we're talking about conditioning, we're interested in saying, well, how close are we to solving this equation? So we've solved f of something is equal not to 0, but to delta f, something small. And what's in here is the root that we want plus some error in the root. Okay, and we want to somehow relate this error, the error in the root that we find, to the little error here, how far away we are from actually making this thing equal to 0. Right, so this is going to be the answer to many, many, many questions this semester. We don't know what to do, we Taylor expand, okay? So if we Taylor expand this, what do we get? We get f of alpha plus delta alpha times f prime, plus something small, is going to equal delta f. Yeah?
Why is it delta f and not f plus delta f?
Why is it delta f and not f plus delta f? It's a matter of a change of sign, so it's not going to be a change in magnitude if we do it that way. But sure, I could have said f plus delta f is equal to 0.
Oh, no, okay, I just meant okay. I thought we were what was doing is the error was the quantity and then.
Right, so we're trying to make f equal to 0. So delta f here is a measure of, instead of getting 0, the error in our data is whatever delta f is. And what matters not so much is the sign of it, but the size of it. I saw another hand, yeah.
Is it given that the function is differentiable?
Is it given that the function is differentiable? So that's a good question. So how well the method you use is going to work is going to depend on the smoothness of the function. And for some things, like if you want to use Newton's method, for example, right, you need the derivative to use Newton's method. If you want to use a simpler method like bisection method, you wouldn't need differentiability. So this will come into the method you use, and it certainly comes into trying to assess how well conditioned this kind of problem is.
Okay, because based on that, we are expanding the.
Yeah, so I think at the least, to have some guarantee of conditioning, you probably at the least want it to be Lipschitz continuous. Right, which is kind of the next best thing to having a derivative. Okay, so what do we get here? We're interested in the ratio of delta alpha to delta f. What is this equal to? This is 0. So this is f evaluated at the true root, which we don't know the true root, but. So if we look at this ratio, delta alpha over delta f, take it in magnitude. In magnitude, it's going to be equal to 1 over f prime of alpha. Okay, so what does that say? If the derivative vanishes, then we might have a problem. As long as the derivative is bounded away from 0, we've got a well-conditioned problem. Okay, that probably makes sense. If I just draw a picture here, right? And this is my f. Okay, And for an f like this, the derivative is, not 0. That if I'm a little bit away from here, so I've gone up a little bit this way, I've also gone to the side a little bit. Whereas if I have something where f is allowed to vanish, or f prime rather is allowed to vanish, I could, maybe this is my root. Over here I've only gone up a tiny little bit, so delta f is small, but this horizontal distance could be quite big because f is just traveling flat. So kind of intuitively it should make sense that 1 over f prime is something reasonable. So for this to be well conditioning, we want f prime to not be 0. Yeah.
Well condition will refer, I just want to the function or to the root finding, to the process. The well conditionness here is of the.
Sorry, so can you say the question again?
Yeah, my question is, you said for us to have a well condition,
Yeah.
we want f prime to not be 0.
To not be
so
0,
that doesn't
right.
blow up. Well condition is an adjective for the root finding solution, the function, the method of finding the root.
So this would be well conditioned for the root finding problem itself.
Root finding process.
So this is independent of the method that we're using. This is just a statement that we want that if our error in delta f is very small, then we want this distance to also be very small. Whereas if we have something flat, we could have a delta f that's quite small. But now we're way out here, and delta f alpha is relatively large. So that's inherent to the problem. I haven't used any method here. Okay, so simple method. Maybe the simplest method I can think of, where I don't need to make assumptions about derivatives or anything like that, is just let's try to sandwich the root and just keep trying to, move this, make this sandwich smaller and smaller until we box it in. That's the bisection method. So if we want to do the bisection method, what do we do? Okay, so again, we have a root finding problem. And we start by picking two guesses that could be very far apart. And the only thing that's important about these two guesses is that f should change sign. Okay, so I might say this is my a naught, and this is going to be my b naught. Okay, so they're not particularly good guesses at the root. But we know the root is somewhere in between them as long as this is a continuous function. Right? And this is where it's kind of important that I make this assumption of continuity, right? Because if it wasn't continuous, it could be negative for a bit and then jump up to positive and never have a root. Okay, so I start by sandwiching it, and then what do? I look for the midpoint of the interval. I say, okay, now the root is either in here or it's in here. And again, I just look to see, well, where does it change sign? Does it change sign in this interval or this interval? Well, it looks like f is negative here, positive here. So this is going to become my new interval. Right? And then I repeat the process. I take this, and this will be my b1. I bisect the interval, and again, I say, well, f is positive in both of these. Changes sign here. So this is going to be my new right endpoint, and I keep this as my left endpoint. Okay, so that's the picture version of the algorithm. If you want to actually tell a computer to do this, you need more than a picture usually. So what do? We start by saying, let's find a naught and b naught such that f changes sign. Okay, an easy way to check if f changes sign is just to multiply these two values together, right? If one's positive and one's negative, then this result should be negative. Okay, and automatically we have a bound on the error, right? So if we say our guess is going to be the midpoint, we know that the root lives in a box of width half of this total interval, right? So automatically, we have this kind of bound. That the difference between the midpoint, if we decide to use the midpoint as our guess at the root, and the actual root is going to be certainly less than half the width of this interval. Say, okay, we call that our guess. So we bisect the interval and say, let's let xk equal, say, ak plus bk over 2. Right? Or this is going to be an iteration now. So we'll do this for k from 0, 1, 2, until we decide to stop. Okay, and then we keep going. So we say now 1/2 of this is going to become our new interval. So we choose a new subinterval. Okay, so we either do ak plus 1 is exactly the same as ak, and bk plus 1 is this midpoint we just calculated, or the other way around. We leave our left endpoint, we update our left endpoint, and we leave our right endpoint the same. Okay, so such that, again, we want a sign change in the middle. And then you iterate, right? Keep going until you're happy that things are accurate enough. I guess something nice about this is, like I said, you have an error bound, right? Because you always have an interval of this width. You know that your root is somewhere in here, right? So you have a maximum of the error. The interval width you're working with is a bound on your error. Even if you have an ill-conditioned problem, right? You know that the root lives in here somewhere. So that's nice. That's easier than you're going to get for most methods. What else do we care about? So easy method to use, right? A couple lines of code in the little loop. Automatic error bound, which is nice. What else do we care about in the method?
How fast it converges.
How fast it converges, you bet. Order of convergence. So let's see if we can work that out. Okay, so we know this. If xk is our guess at the root, and we want to compare it to alpha, we said we have an error bound. The error bound is always the width of this interval. And the size of the interval gets cut in half every time, right? So when this was 0, it was b0 minus a0 over 2. When k is 1, it's going to be divided by 4, and then divided by 8, divided by 16, so on. Always dividing it by a factor of 2. So we can very easily write down this error bound over 2 to the, okay, and then we just divide by 2 as many times as we've bisected the interval. Okay, what do I have to look at to determine the order of convergence? Jake.
Limit as the ratios.
Ratios of what? Yeah.
So it should be the error at the k plus 1 term.
Right.
The error at the k to the power of alpha.
That's right. So we want to look at the ratio between the error at the in the k plus 1 term to the error in the kth term, possibly raised to some power. Exactly. So we need to compare this to xk plus 1 minus alpha, basically. So if we do that, well, xk plus 1 minus alpha is going to be bounded by the same thing divided by, I'm going to write it like this, times another factor of 2. All right, and if I take this and divide it by this, I'm going to get a constant coming out, just 1/2. Okay, so if I do that division, xk plus 1 minus alpha divided by xk minus alpha, we expect it to be sort of a ballpark, let me call it this, ballpark to be less than 1/2. All right, so in this case, the best we can expect is linear convergence. Of course, you could get lucky. You could bisect the interval and land exactly on the root when you do it, right? That could happen, and then you'd be completely done. But in general, in general, we could hit this worst case limit for general problems. So this kind of ratio is the best that we can hope for. So what do we expect? We expect then linear convergence. And I guess another bonus of this, it's essentially global convergence. So what I mean by global convergence is you don't really need a good initial guess, right? These can be very far apart as long as we have a sign change. So that's nice. You don't need a good initial guess. It's easy to use. You get error bounds. The downside is it's not super fast. So I call this a safe method. Very safe method, but not necessarily good if you're in a hurry. So if we wanted to go faster, here, what did we do? We didn't use very much information about f. We didn't use information about the shape of f or the values of f, only whether it was positive or negative. And that's not much info. If we want to build a faster method, we need to build in more information about how f is shaped. Yeah?
Sorry, just to go back to the linear convergence thing.
Yep.
If the result of this would have been something that wasn't constant, then would we have gone back and
Yeah, so if this wasn't a constant, then we might have said, we should try to look at this to some power.
okay, and then whatever power that is where you get a constant.
That's right. Whatever power that is that will give you the constant, that will give you your order of convergence.
If we try to generalize it like taking to the power beta.
If I try to generalize it by taking this to the power of,
As value of xk minus alpha to the power beta.
yeah. So if I try to take this to the power of beta, what's going to happen? I'm not going to get all of this cancellation, right? I'm going to still get something on the right-hand side that involves k. And so we're not going to limit to a constant.
It will be in 2 to the power some beta.
It'll be 2 to the power of some beta, yeah.
When beta is 1, then the limit is defined.
When beta is 1, then the limit is defined in this case. That's right. Okay, so let's try to build some shape info into here. So the simplest piece of information we have about shape is the derivative. So to speed this up, let's use information about the shape of f. Right, so one way to think of that here is, in this case, if I was over here, I said f is negative over here, and f is positive over here. So if I'm starting from here, I know I need to move in this direction to find the root, right? That was just using information about the values of f, or the signs of f. Now, if we build in some of the shape information, we might ask, well, okay, I know I need to move in this direction, but how far in this direction should I move? Instead of just saying, let's hit the midpoint, maybe I can make a more clever guess about how far in this direction I should move, and I can do that because I know how f is shaped. So this is Newton's method. And again, there's a fairly easy picture of how Newton's method works. So I have some function I'm trying to find the root of. I start with some initial guess. Let me give this a little more curve. Okay, so I'm down here. I know I'm not at the root. Now what am I going to do? I'm going to use not just where I am, but I'm also going to use the slope of f at this point and say, let's try to approximate this by its tangent line. So if I draw its tangent line, that looks something like this. Straight lines are easy to work with, right? Solving f of x equal to 0 is hard, but solving L of x, a line equal to 0, is easy. And I can say, okay, that hits 0 here, so let me use that as my next guess. Right? And then I do the same thing. I say, okay, f of x1 is up here. Let's draw the tangent line and see where that hits 0. And that becomes my x2. Okay, and in 2 steps, on the picture in 2 steps, this is already getting me pretty close. And you can see that in the next step, I'm actually going to get about as close as I can get on a picture with this size of marker, which is certainly better than what we had over here doing bisection. That's not a proof. The picture proof is not a proof, but it's nice to have some intuition. So again, let's write down what this algorithm looks like and see if we can try to do some more rigorous analysis than just the picture proof. Okay, so we're given this guess, xk. So we linearize f. Okay, and we say that, well, if we do that, what do we have? L of x is equal to f of xk plus x minus xk times f prime of xk. And we're going to set this straight line equal to 0 and solve for x to get our new guess at the root. Okay, so if I say we're going to assume that L of xk plus 1 is equal to 0, I can solve for xk plus 1. Right, and it's my old guess minus the ratio of the value of f to the derivative. Okay, and this you've seen before. What you may not have seen before is some of the analysis that goes into how do we know this converges and how do we know how fast it converges. So I'm going to do things out of order a little bit. I'm going to start by saying if it converges, what's our order of convergence? Okay, and then we're going to use some of that information actually to go back and actually do a proof of convergence. And it's often easier to take the steps in this order. So let's start by saying if it converges, how fast will it be? Okay, so again, I need information about xk plus 1 minus alpha. And ideally, I would like to relate it to what xk minus alpha does, so that if I put the right power here, we get some nice cancellation and find some sort of constant popping out. Okay, so we know we need xk plus 1 minus alpha. We know we need to relate it to xk minus alpha, so the obvious thing to do here is put in Newton's method, right? Just put in what this is from Newton's method. So what do I have? I have xk minus alpha minus f of xk divided by f prime of xk. Okay, right now, there's no obvious way to pull out a simple ratio of this to this, so we need to do some more manipulation. So the manipulation on these problems is basically always going to go something like this. This is a simple method, but we're going to Taylor expand everything in sight, basically. So I'm going to pull everything over a common denominator to start. So if I do that, what do I get? I get minus f of xk. So that's this term. Then plus f prime xk, xk minus alpha, divided by f prime of xk. Now what does the numerator look like, or almost look like? So yeah, we've got a function value, we've got a derivative times some difference. Where do you see things like that? Yeah.
The LX on top.
The LX on top, yep. So that's, yep, Kathleen. Yeah. So yeah, we're seeing this linearization, you're seeing the mean value theorem, you're seeing really a first order Taylor approximation. Okay, so I can make it a little more obvious that this is a first order Taylor approximation. Let me pull this minus out. I have f of xk plus f prime of xk, and I swap the sign here. So here, this looks like a Taylor expansion about xk, where I'm trying to approximate f of alpha. Right? So function value at xk plus derivative of xk times alpha minus xk. That's a first order Taylor approximation. So we know that that's going to be equal to f of alpha plus some error term, right? And this is where we need Taylor remainder theorem. Okay, so if I simplify this a little bit, this was f of alpha, okay, and then minus my error term. So f of alpha is equal to this plus error, so this is going to be f of alpha minus the error term. So we're going to subtract off our error term here. Alpha minus xk squared times f double prime evaluated somewhere. And so at first blush, it maybe doesn't look simpler, but it is simpler because I've got this f of alpha in here. Bringing f of alpha in is great because it just goes away. So what do I have? I have some numbers times alpha minus xk squared. That's my old error squared. So on this side, I have something involving my old error. On this side, I had something involving my new error, and that's what I wanted. I wanted to be able to relate them to each other. What's the order of convergence that you're going to guess at from here? 2, exactly, right? Because this is showing up as an error squared. So if I rearrange this a little bit, what do I have? I have xk plus 1 minus alpha over xk minus alpha squared is f double prime somewhere over 2 times f prime. And now we're interested in what this does, right? In order to actually look at order of convergence, we're interested in the limit. What happens when k is large? So I started by saying, let's assume that it converges. So if it converges, and if these functions are nice, if these are continuous, right? Well, ck is sandwiched between xk and alpha. If xk is going to alpha, ck is also going to alpha. Xk is going to alpha. So this limit of all of this is going to be nothing but f double prime of alpha over 2 f prime of alpha, under the assumption that the first and second derivatives are continuous. So if f is a C2 function. And clearly for this method, it's going to matter that f prime is not vanishing, right? Bisection method doesn't really matter if f prime vanishes or not. This method, it definitely matters. Yeah.
So is it fair to say you've gained speed, but we've limited the scope of the method?
We've gained speed, but we've limited the scope of the method. That's fair. Absolutely. So nothing is free. Anytime you want to gain something, you want to gain speed, you're sacrificing something else. So it's that's what I'll say. There's no one-size-fits-all method that's best for all problems. It depends on your problem and what you need. Yeah. We're going to use Taylor expansions to analyze, a lot of these methods. So with the bisection method, what do we need? We're not incorporating derivative information, right? So essentially, we're just doing 0th order Taylor expansion. Yeah, so how far you need to Taylor expand is going to depend on what method you're using, certainly. So here we needed first order Taylor expansion, and then our error lived in the next highest derivative. Okay, so we expect quadratic convergence here. If it converges quadratically. Okay, so we'll say if f is C2 with f prime alpha non-zero. That's not a proof that Newton's method works at all, right? I started with the assumption that I could take this xk to alpha, right? I've never proved that to you. I drew a picture where it looked like it worked, but a picture is not a proof. So we know if it converges, this is what we get. I'll say everywhere up to this step was valid reasoning, right? It was this line where I used the assumption of convergence. So everything up to this step I can reuse up till now, but if I want to prove convergence, I have to stop here. So let's try to fill in some of that gap. Okay, so we want now to prove it actually converges. So is it true, or under what circumstances is it true? So I'm going to write the result first, and then we're going to try to prove it. So we're going to need the assumptions that we used here. Let f be a C2 function. It has a root. Okay, so I'm assuming it's a well-posed problem, right, that there actually is a root. Okay, so at the root, of course, f of alpha is 0 by definition, and we're going to ask that f prime be non-zero. So what does the convergence theorem say? The convergence theorem says not just you can start anywhere. The bisection method, you can start almost anywhere as long as you hit a time change. Newton's method is going to ask that we start close enough to the real solution. This is vague on how close is close enough. So what it says is that once you get close enough, you're in business. So there exists delta greater than 0 such that Newton's method converges. Okay, to the root, as long as we start with an x naught that's close enough to the root. Okay, so delta tells us how far away from the root we're allowed to start. As long as we start within this window, Newton's method is fine. If we start outside the window, then we don't know. Okay, so let's see if we can work this out. All right, I'm going to, in the interest of keeping the writing down, I'm going to define I to be this interval. Now, we have to sort out exactly what this interval should be. And now, what do we know? Okay, here's our root. We know the root exists. We know f prime is not 0 at the root, right? We also know that the derivative of f is continuous. That's built in here. F has continuous first and second derivatives. So f prime is not 0 at the root, and f prime is also not 0 in a neighborhood of the root, right? Eventually, it can become 0, certainly, but as long as we stick close enough to the root, it's not 0. So I can say, maybe I'll let this be my window. As long as delta is small enough, okay, f prime is not 0 in this interval. Okay, that's important, right? Because if I ever had a guess along the way where f prime was 0, Newton's method would just blow up on me. I'd be dividing by 0. And that's bad. Okay, so we can say, first of all, that if we start with a small enough interval, f prime is not 0, and Newton's method is at least well-defined. And that's the first good part of any good method, is that it's actually a well-defined method that's not just going to throw out infinities at you. Now, what else do we want? We know we want x naught to start in this interval. And when we compute a new guess, x1, we'd like x1 to stay in this interval. And when we compute x2, we want x2 to stay in this interval. So we need to show that. We need to show that our Newton's method is going to not wander out of this interval, because if it wanders out, then we're in trouble. Okay, we can use this result. It's always, if you're stuck on a proof, just start writing down the things that you know. That's a good place to start. You have definitions. You can write them down in terms of epsilon deltas if you need to. So I'm just going to recall, we know this already, that xk plus 1 minus alpha is equal to 1/2 of xk minus alpha squared times f double prime of ck over f prime of xk for some c, and we know that this number is bounded. Yeah, Jake. Does the c have to be in the interval? Yeah, so when we did this calculation, we said xk was in here. We were Taylor expanding about xk to approximate f of alpha. So the ck will always be between xk and alpha. And that's from Taylor remainder theorem. So yeah, that's of course important. This we don't know what this number is. It's something, but it's bounded, right? Because, why is it bounded? Because f is c2. Right? F has continuous first and second derivative. So if I just limit myself to an interval, I know that f prime is not becoming 0 in this interval, then this certainly is bounded. Okay, so as long as we stay in our interval. And m is just some constant. Maybe it's big, I don't know, but it's a constant. Okay, so let's try to verify that xk plus 1 stayed in this interval. right? And if it stays in the interval, we're in business. Newton's method is well defined, and I can keep using this estimate iteratively, right? I could put an xk plus 2 here and xk plus 1 here, and it would still be valid. But it's only valid if I know that this guy still lives in my interval. Okay, so let's see what we can do. Let's say that we're given xk minus alpha is in the interval. In other words, this distance is less than delta. My interval has width delta. So what do we know? Xk plus 1 minus alpha, we said is less than or equal to 1/2 m xk minus alpha squared. And this, right, we said this is bounded by delta. Let me actually, sorry, I'm going to absorb this half into the m, just to make things a little bit cleaner. So if m is a constant, m over 2 is also a constant. Okay, so we know this is true. Now what do we want? We would love to be able to say that this difference is also less than delta, right? So if we can guarantee that this is less than delta, this is automatically less than delta. So I'm going to say this with a question mark. Can I make this less than delta? Close. Delta less than 1, almost. Less than 1 over m, exactly. So m delta squared is less than or equal to delta. Okay, if I divide out a delta, I have m delta less than 1. That's going to be my restriction. So this works as long as m delta is less than or equal to 1. Okay, so what does that mean? As long as I pick my delta small enough, I'm in business, right? Again, if I pick my delta too big, this estimate's not going to hold. Now I've said as long as delta is small enough, derivative doesn't vanish. Now I also have this requirement, which means, well, maybe I have to shrink this a little bit more. But still, there's a positive delta that makes this work. Okay, so if delta is less than 1 over m, then xk plus 1 indeed stays in the interval. Believe this? Okay, so we're in business. We have a method that is well posed. We stay in this interval. Now, we just need to make sure that we're not just bouncing back and forth in the interval and never getting closer to alpha. Was that your question? Okay, good. It was a good question. Okay, so we need to do a little bit more. We need to know not only that this stays less than delta, what we actually need to show is that this difference goes to 0 as k goes to infinity. That's what we need to show for convergence. But now I'm in business. I can start using this estimate iteratively. So what do I know? I know that xk plus 1 minus alpha is less than m delta squared. So we know that. Okay, and we know this is true for all values of k now, because we always stay in the interval. And as long as we've stayed in the interval, this estimate is valid. Okay, I'm going to multiply both sides of this by another m, and just to have a little bit of symmetry here. You don't have to do this. Or I could also say m xk plus 1 minus alpha. I can loosen this up a little bit. I don't have to put a delta here. I could use my old guess here. It's less than m xk minus alpha all squared. And now I can keep going with this estimate, right? So let's see if we can take this back, right back to our initial guess. I can bound this in terms of the error at step k minus 1, right? Same estimate works. So again, all of this k minus 1, it gets squared, and then it gets squared again. So now we're to the 4th power. Okay, again, I could go back to k minus 2, and it would just get squared again. I could go back to k minus 3, it would get squared again. So we can keep going with this all the way back to my initial guess. Okay, and now we've squared this k times. So k minus 0, we squared it once. K minus 1, we squared it twice. K minus 2 times, we square it 3 times. So k minus k times, we square it k plus 1 times. Okay. This follows from a proof by induction. It's immediate. I'm not going to write it out.
That is 2 times k plus 1 or 2 raised to the
2 times k plus 1. Yeah. All right, so this was 2 times 1, 2 times 2. The next step would have been 2 times 3. Yeah.
Oh, and then was the M was determined by an interval.
The m was determined by our interval, so it's not changing. Yep. Sure, you want to show that a sequence is convergent, you can show that it's a Cauchy sequence. Okay, so now we're interested in, for convergence, we're interested in what happens to xk as k goes to infinity. Now, we can find out what happens to xk minus alpha as k goes to infinity, and what does that go to? Well, let me put one more step here. This lived in our interval, so this was bounded by m delta to the 2 k plus 1. This thing in here was less than or equal to 1, and if we sharpen that up a little bit and say let's make it less than, strictly less than 1, then what's going to happen to this term as k goes to infinity? It vanishes, exactly. So as long as we chose m delta to be less than 1, xk plus 1 minus alpha is going to converge to 0 as k goes to infinity. And that's completely equivalent to saying xk converges to alpha. Okay, so Newton's method works. You've probably been using it for years now. You can kind of put your mind at ease that actually this wasn't a completely crazy thing to be doing all this time. But are there any questions on the proof? You can do a proof like this, right? If I give you a different method, you can do the same thing. Yeah.
So we want MD to be less than 1.
M delta to be less than 1, that's right.
So over here, we didn't need it, or was it just a typo? MD less than or equal?
So there's going to be multiple. So for this step, I guess, we only needed it less than or equal to 1.
Right there, yeah. Is that less than or equal to, is that equal to?
This is less than or equal to 1.
Equal there, but not up to
Yeah, so for this step, to make this step work, to make sure we stayed in the interval, equality was okay, it was allowed.
Okay.
For this step, it's not okay because if we have 1 raised to a large power, we're still at 1, right? So along the way, and you'll have seen this in an intro analysis course when you're going through, here's my epsilon, I'm trying to find the delta to make all this work, and as you go through, you come up with extra conditions on the delta, and then you pack them all together at the end and say, well, delta is a minimum of 1 and epsilon over 2 or whatever. It's the same thing happening here. We're coming up with multiple conditions on our delta, and then we just make sure the smallest one is still a finite number. Great, we're in business. We've satisfied all the conditions.
Thank you.
Yeah.
Perhaps it's getting ahead of ourselves or sideways, but a function that has multiple roots?
Function that has multiple roots. Yeah, so there's different things you can, so you can start by, actually you'll get to play with this a little bit in the homework assignment too. But what you typically expect is that with Newton's method, you can converge to all of them, but you need an appropriate initial guess. So which one you converge to will depend on your initial guess. Then there's other things that you could do. Once you've, okay, I found one root, I try to somehow factor it out of my function so that I don't find it again. So there's tricks for doing things like that.
And similarly to the bisection method?
Let's see. The bisection method will be harder to deal with multiple roots, I think. 'Cause all you know that there's something in here. I mean, there could be one root or there could be an odd number of roots in there, and you don't really have a way of being able to tell that with the bisection method or easily factor that out. So pros and cons. Quadratic convergence, which is wonderful, it's fast. And, as long as you start in your little interval with delta, basically each iteration you're doubling the number of significant figures you have correct. So that's great, that's fast. It means you need only a small number of iterations. The downside is, it depends how big this delta is. Sometimes you need a really good initial guess, and that's hard to find. So sometimes you got to string methods together. You might say, let's do a few iterations of bisection method, and then say, now we have a good enough guess that we can switch over to Newton and accelerate the convergence to the end. So you can certainly combine methods that way, and we certainly have to do that sometimes. There's other tricks for trying to expand the region of convergence for Newton's method. You can take smaller steps. Instead of going the entire f of x over f prime, you can only go half that distance. And taking smaller steps, you can get away with a worse initial guess sometimes. So there's certainly tricks, and there's certainly downsides to Newton's method. You also need to know the derivative of f, which if I just give you a simple scalar equation, solve cosine of x is equal to x, you can compute the derivative of that. If the function you're trying to find the root of requires you to solve a differential equation and then extract one part of that and interpolate it onto something else, and that's how you compute f of x, you might not be excited to compute the derivative of this function, right? So there's always pros and cons. That's Newton. What else could we do? Newton's method said, let's approximate the derivative by a tangent line. What's another natural way to approximate the derivative? Using the secant line, yeah. The advantage of a secant line is you don't actually need to know the derivative of f, right? You just need to know the value of f at 2 points, and then you draw a line between them. So that's another option. Okay, approximate f by not a tangent line, but by a secant line. Right, so we start with my x naught. Now, for a secant line, I need more than one initial guess. Right? So I'm going to do a secant line. Well, I need to connect this to some other point on the graph. So there's still, you need one way or another two pieces of information. If I'm going to build in shape information of f, I need extra information. So that can come from knowing the derivative, the function value and the derivative, or from knowing the function value here and the function value somewhere else. Somehow we have to build in extra information. So if I do that, right, then I would draw the secant line between these two. And find where that intersects. And on my picture, I've converged in one iteration. That will not always happen in real life. That's just a function of this particular picture. So here, again, we need two pieces of information to kick off the method. So given xk minus 1 and xk, okay, I draw the secant line. I say L of x is equal to f at one of the points, and then my slope is rise over run. Okay, and then I have x minus xk. Okay, and then from here we do the same thing that we did before. We say we are using this straight line to approximate f. Let's set the straight line equal to 0. And solve for xk plus 1. That gets us our new guess. So then what do we have? Xk plus 1 is equal to xk minus f of xk. And then we got to take the reciprocal of this slope here. It actually feels the same kind of as Newton's method, right? Newton's method was xk minus f of xk divided by the derivative. And now this is divided by some approximation to the derivative. Okay, this is going to be simpler to use in the sense that we don't need to compute derivatives of f, which can be very good in some situations. You've got to have a little more you've got to store more past information, right? So once I update xk, I can't throw out my old guess. I have to keep it for one more step. So you need to store a little bit more information. Right, with Newton's method, once I compute xk plus 1, I can throw out xk. I never need to know it again. With this, you can't do that. You have to keep it for one more step. But again, we should be asking, well, how fast is this really? So again, what's the order of convergence? So I think I'm going to do the order of convergence calculation here, but not the proof of convergence calculation. The proof of convergence calculation is exactly the same as it was for Newton's method. It's getting the order that's a little bit more work and kind of a little bit interesting. But we start the same. We start by saying, well, I need to know how this relates to my last guess. So I'm going to put in what the method tells me to do. So xk minus alpha minus all of this. Okay, and again, we're going to kind of pack it over one common denominator and see if we can try to simplify these a little bit. And simplify means that we really want to get things in terms of, xn minus alpha kind of terms. Okay, so let's see what happens here. Well, we've got an xk times fxk minus fxk minus 1. We've got an alpha times the same thing. Okay, and then I've got an fxk times xk minus xk minus 1. Okay, some terms are going to cancel on us. So we have xk f xk, no minus xk f of xk. Then what do I have left? xk f xk minus 1, fxk, and an xk minus 1. And I have the same f terms here being multiplied by alpha. So what am I going to do? I'm going to collect the fxk terms. I'm going to collect the fxk minus 1 terms. Right, so this product is going to go away. This product is going to go away. Let's collect what's left. And what's left is, okay, the fxk terms involve, let's see, an xk minus 1 and a minus alpha. Okay, and the fxk minus 1 terms are going to involve the same kind of thing, minus xk and a plus alpha. Okay, so if you were standing up here in my shoes, what would you do next? So I can't quite factor out the xk minus alpha because this is k minus 1 and this is k. That's what I want to be able to do. I want to be able to kind of factor these things out. But we're not quite there yet. But I got to manipulate this somehow to get myself there. Add something and subtract something. Add something and subtract, so they're both linear approximations. You want to bring in an f prime somewhere. Okay, good. I like this suggestion. What's a good way to bring in an f prime? Taylor series. There it is. So you're sitting here, and you have some expression you have to manipulate, and there's nothing, you've kind of used all the pieces of information you already have, which I didn't have much to work with. I only had this formula to work with, and I already used it. Taylor expansion is your friend, right? So let's try to Taylor expand things a little bit. Okay, so here, what am I going to get? I have my x, k minus 1 minus alpha. Now this, I can Taylor expand about alpha. So I get f of alpha, which is 0. I get f prime of alpha times xk minus alpha. I brought in the derivative. And then I have my error term. So f double prime of, let's call it eta 1, times xk minus alpha squared. Let's give ourselves some more space to work. Okay, and I can play the same game over here. So we Taylor expand about alpha. So I get f of alpha, which is 0 because that's my root. Bringing in f of alphas is great because they just go away. Okay, I get f prime alpha times xk minus 1 minus alpha. So I brought in the derivative, and then I have some error. And now I have some like terms that will cancel, exactly. Right? So here I have, what is going on with my f prime alpha? It's multiplied by an old error and a really old error, minus. And here it's, again, multiplied by an old error and a really old error. So those go away. So whatever's left is going to live in this second derivative, right? Which now involves, okay, this squared times this, and now this times this squared. There's some common terms that we'll factor out at least. Okay, and then in the denominator, okay, I could do the same kind of thing. I can Taylor expand these or just recognize that I've got a bit of a mean value theorem going on here already. Right, so this is the same as xk minus 1 times f prime evaluated somewhere. Okay, so again, Taylor expansion is a really good tool for a lot of this error analysis. Okay, it can be a bit of trial and error to decide how far do you need to Taylor expand. If you Taylor expand a bit and if things cancel out so much that you have nothing useful to work with anymore, then you might say, hey, let's try expanding a little bit farther. You know, if I expanded to third order and I said, well, all the cancellation is happening in the first order terms, and I might go back and say, maybe I don't really need those third order terms. So, you know, it's trial and error, but what we want to see is simplification, and what we are seeing here is some simplification because we get this nice cancellation. What do I get at the end of the day? I get an xk minus 1 minus alpha term that's common to everything. That I can factor out. I get an xk minus alpha, sorry, it's this xk minus alpha term that's common to everything, and that I can factor out. Okay, and then what's left? What's left is half f double prime 801 and one more xk minus alpha, and then half f double prime 802 and xk minus 1 minus alpha. Divided by I'm going to write f prime over here. And I'm going to write this in a way that kind of mimics the terms I've got going on here. So why am I doing that? I don't really like having this difference in the denominator here, right? I want xk minus alpha kind of terms, okay? So this is an xk minus alpha. This is an xk minus 1 minus alpha. I'm happy with those. This is a constant. I don't mind, or you know, it will converge to something that's a constant. I don't mind having that floating around. I don't really love having this difference floating around, and I'd rather write it in terms of xk minus alphas. Okay. So all this looks a little bit messy, but it's actually going to simplify really nicely. So let's just say I decided to write this as lambda 1 equals xk minus alpha, and lambda 2 equals alpha minus xk minus 1. That's the negative of this. And I note that the denominator is actually the sum of my lambda 1 and lambda 2's. So what do I really have here? I have an xk minus 1 minus alpha, xk minus alpha. I'll pull out this 2. And now I have, okay, lambda 1 times f double prime 801, lambda 2, lambda 2 is the negative of this, over lambda 1 plus lambda 2. Okay, what does this look like? Do you recognize this? So what if I happened to know that lambda 1 was equal to a half? What would it look like?
Error.
So you think error. So let's go think back to actually just simpler mathematics. A midpoint, yeah, or an average, right? So what is this? This is a weighted average. So here I'm saying some weight times f double prime 1, and some weight times f double prime 2, and my weights are going to sum to 0 because I've divided by the lambda 1 plus lambda 2. So this is actually an average. So what do I have? I have that f double prime is some continuous function, and I've got, say, this is my eta 1, this is my f double prime eta 1, and maybe this is my eta 2, and this is my f double prime eta 2. And now this is some value in between those. It's some average of them, right? So it's some value in here. Let's call it mu. I don't have room to write the entire average there. So it's a continuous function. We found the value at 2 points. Now we pick a number somewhere in between those values. What can we say about that number? F is going to, exactly, f double prime is going to achieve this number somewhere. So I'm going to call this eta, right? That's our intermediate value theorem. So this says that I can write this as xk minus 1 minus alpha, xk minus alpha, times f double prime somewhere, divided by 2 f prime somewhere. Okay, so that's simplified down. It looks like almost what we got for Newton's method, except instead of xn minus alpha squared, we have a recent one and a previous one. Which kind of reflects the nature of the secant method. Assuming it converges. Exactly. So we're assuming this converges. It kind of looks like Newton's method. We can't quite conclude quadratic convergence here. But again, let's take this number here, right, to be bounded by some constant, f is C2. And what do we know? We know now that the error after step k plus 1 is less than m times the error at step k times the error at step k minus 1. Okay, we can use the same argument as before to say that if we start, comma in between, with these being less than delta, so if we start in a window of neighborhood delta, then we're going to stay in a window of neighborhood delta. Okay, again, using the same argument as before, if m delta is less than or equal to 1. So most of this proof, this was the hard part, just figuring out how to manipulate and simplify things. But most of the proof goes the same as it did for Newton's method. We stay in the interval as long as the interval is small enough for the same reason as Newton's method. Now let's try to pull out an order of convergence. So let's define epsilon to be equal to this m delta. Okay, so we have m e naught is less than or equal to m delta. We have m E1 is less than or equal to m delta. They both started in the interval. And if we keep going, ME2 is going to be less than or equal to, ME2, right, based on this, is less than or equal to ME1 times ME0 which is less than or equal to epsilon squared. And again, we keep marching this forward. This is using the last two error bounds. Now this is where things get different than Newton's method. This one was an epsilon squared, but this was only epsilon, right? So this was an epsilon cubed. What will my next one be? To the fifth, exactly. So we're always going to be adding the previous two exponents together. Okay, so in general, if we say that m epsilon k is less than or equal to epsilon to some power that depends on k, we figure out this power by adding up the previous two exponents. So what numbers are we going to get as our exponents? Do you recognize them? What's that? Fibonacci sequence, exactly. So here, qk is equal to qk minus 1 plus qk minus 2. It's a Fibonacci sequence. Okay, we do what we did last class or the class before, whichever it was. We say we have a recurrence relation. We can look for solutions of the form beta to the k and solve for beta. Remember we did that? We got two solutions for beta, and we took a linear combination. So if we do that here, we get qk is equal to 1 over root 5, 1 plus root 5 over 2 to the k plus 1, minus 1 minus root 5 over 2 to the k plus 1. This guy's bigger than 1 in magnitude, yes? 1 plus root 5 over 2. Okay, this is bigger than 1. This is less than 1 in magnitude. So as k gets large, this term goes away, and we're basically being dominated by this term. So we're going to say this is approximately 1 over root 5, 1 plus root 5 over 2 to the k plus 1 for large k. Where did I get which? Q sub k? This Q sub k? So here, this was by saying substitute in qk equals beta to the k. Sub it into the recurrence relation and solve for beta, just like we did last class. So can you see from this what our order of convergence is going to be? So what are we going to have? We're going to have the error after k terms is bounded by 1 over m epsilon to the qk. Which is approximately 1 over m epsilon to all of this power. And this looks like the bound I had for the previous error. Right? This is qk minus 1. All of this with the k plus 1 is qk. With just the k here, qk minus 1. So this is going to be approximately 1 over m times m to the e k minus 1. Right? So epsilon to the qk is approximately equal to the kth error. This is epsilon to the qk minus 1. Right? All I've done is drop the k by 1. This is approximately equal to the k minus first error. So what's the order of convergence? What's that? It's higher than 1, but lower than 2. It's 1 plus root 5 over 2. So 1 plus root 5 over 2 is the order of convergence. It's the golden ratio, exactly. Why you get the golden ratio out of this, I don't know. Oh, it's kind of mysterious. But we get the golden ratio out of this. So it's a superlinear convergence. It's not as fast as Newton's method, but it has the, some advantages. We don't need to compute derivatives. So I'm going to leave you there. We're going to look at more general fixed point methods next time.